So from now on, the state of a system will be a vector consisting of two or more numbers rather than just one number x. So the state will be something like x and y. So a vector like this, I might often put it in a column vector. Maybe I'll put it in an ordered pair like this. I'll treat these basically as the same. And the beauty of the general theory that we're going to eventually be studying after today's lecture — today will be a little bit specific to the 2 case, but after today's lecture, a lot of the things we do will pretty much apply to two-dimensional systems where the state is described by 2 numbers, just as well as they apply to higher dimensional systems, 3, 4, etc. So it turns out that a lot of the complicatedness of going from one dimension and then increasing the dimension from what we were doing, it turns out that a lot of the complicatedness you experience in the transition from 1 to 2, and then it does not get much more complicated when you go to 3 to 4, etc. So we're sort of going to work, we're always going to work in this chapter with systems with 2 unknown functions, because the understanding the examples with just 2-dimensional systems, 2 unknown functions, is going to be pretty much enough to be able to handle the higher dimensional versions of things. At least in theory. The computations are going to, of course, explode in complexity often when you increase the dimension. All right, so great. The state of a system is this 2-dimensional vector now. And so where do we imagine these 2-dimensional vectors as living? In the 2D phase plane. So we're upgrading from differential equations to systems of differential equations, and we're upgrading from the phase line to the phase plane. So we've now added an axis. It's now the phase plane. So a state of the system is going to be something you interpret as a dot somewhere in the phase plane. So here's one state, here's another state, here's another state, here's another state. And at different times, the system will take on different states. So when you imagine the solution to a system of differential equations, imagine an animated dot. So you have sort of a dot representing the initial condition, and then the dot moves around as the system evolves. Maybe x becomes very big, it moves that way. Maybe y becomes very big, it moves that way. Maybe both become very big at the same time. Maybe x becomes big quickly, but y grows slowly. Maybe they both oscillate and it goes around in a circle. Maybe they both oscillate, but with ever-decreasing amplitude, and it spirals in. There are all kinds of things you can get in the phase plane. So a solution, so while a particular state at a particular time, like what is the state right now, while a particular state is going to be a dot in the phase plane, a solution to a differential equation, like the kind of thing that you would use to make a prediction, will be a pair of functions, x of t, y of t, right? Solutions will be this type of thing. So where previously solutions were you've got x as a function of t, now you've got x and y as a function of t. And this represents the kind of animated dot moving around thing that I'm talking about. So at time 0, you've got x of 0, y of 0, that's a dot somewhere. Then as you play time forward, you see the dot move to another place, to another place, to another place. And if you play time in sort of a continuous fashion, you see the dot moving around. So solutions are going to be trajectories in the phase plane. If you may have heard this called parametric plots or something like that, plotting 2 functions of a parameter t. Sometimes I remember in my high school they called it parametric plotting, and I just thought it was some random kind of plotting, and I pretty much ignored it. But it's actually really, really crucial to understanding what it is that you're looking at when you have multiple functions of one variable. This is what you have. You have trajectories in a higher dimensional space. So you could also look at what's called time series plots. So you could look at a plot of t versus x, right? And a plot of y versus t versus y, right? T versus x and t versus y. And you can plot those. But more something that's more true to what it is you're trying to describe, which is you're trying to describe at any given time what is the state of a system whose state is given by these xy pairs. Something that's more true to it, to that, the thing that you're trying to describe, is the plot of a trajectory in the phase plane. So that's where I'd look first, and then afterwards maybe you can look at the time series plots. So previously, what was a differential equation, at least a first order differential equation, was something like x prime equals function of x and t, right? Well, if we explain or interpret the notation correctly, we can basically still say this, as long as we now treat x as a vector valued thing. So let me just put a vector symbol above x here, and let me put a vector symbol above the f. And then this is still what a differential equation is for us, except now interpret x with a vector symbol above it as actually standing for two things, x and y. So it stands for this vector value. I might just call it x vector. This is a pretty confusing looking notation because I'm using x for two things. I'm using x to refer to the first coordinate in these pairs, in these vectors with two entries. I'm using x to refer to the first entry, but then I'm also using x to refer to the vector as a whole. I hope this doesn't confuse you too much. Whenever I use x to refer to the vector as a whole, I'll put this symbol above it. All right? So how is it that this describes a system of differential equations? Well, what is meant by x prime? So if you have a function x vector of t, that's a way of saying you have a function with two component functions, x of t and y of t. Then when we say x prime of t, we're talking about this. That's what we're talking about. When we say f of x and t, so if I just say f with no vector symbol above it, then this would be like a scalar valued function. But if I put a vector symbol above it, then it's actually like I'm talking about two functions here. So that's what's meant when I put the vector symbol above the f, is I'm saying it's a two-component object. Just like when I put the vector symbol above the x, I'm saying it's a two-component object. Or maybe not two, n-component object, depending on the size of things. But let's set everything to 2 for these examples. So f with a vector symbol above it is a two-component object, has two component functions. Now, what about this x with a vector symbol inside? Well, you can unpack that x and view it as, let me make some space. You can unpack that x and view it as sort of x and y. Right? That's what x with a vector symbol means. It doesn't matter if you write it vertically or horizontally. That only matters when you go trying to multiply matrices and stuff, but here it does not matter. So it's just sort of a way of saying that f1 depends on x and y and t, and f2 depends on x and y and t. So a quick way of saying that is to just stick the vector symbol x there. All right, so you see what this is saying then? The left-hand side here is this two-component object, x prime t, y prime t, where x of t and y of t are the unknown functions that you're interested in. And then the right-hand side is just a compact way of writing out that you have actually these two component functions. And now the so-called system of differential equations looks like just one equation, except instead of being an equality of numbers or scalar valued functions, this is now an equality of vectors, or rather vector valued functions. So if you want to, you can always erase the brackets and then just, instead of writing one equal sign, write two equal signs. You can do that because two vectors are equal if and only if their components, their corresponding components are equal, right? But if we can, we will usually actually prefer to write it as one vector equation, because packaging things together to the extent that we can will really help us to use the linear algebra theory that we will need to use pretty soon. So definitely whenever you can, package things together like this. View it as one vector equation. This is our differential equation system. So this is the kind of thing that we're interested in studying here in Chapter 4, probably for the rest of the quarter. All right, so we keep seeing this vector showing up, the vector whose components are these two derivatives, x prime and y prime. So what in the world is this thing? How do we interpret this in the phase plane? Remember, the phase plane is important because the dots in the phase plane are the different states that our system can have. And a solution to a differential equation system, or a prediction as to what a system is going to do, will be a trajectory in the phase plane. So whatever we can visualize in the phase plane, that will be helpful. If you look at the differential equation, there's this x prime, y prime vector. How do I visualize that? Would that also be a dot in the phase plane? Certainly not. It's not a dot, since the axes on the phase plane are x and y, not x prime and y prime. So what is x prime and y prime? Well, to interpret x prime and y prime, you need to imagine that you're looking at a particular solution trajectory. So let's say you have a particular solution trajectory like this. And I'm going to put an arrow on it to indicate which way is forward time. So maybe the dot starts here at time 0, and then as you run time forward, it moves around and does that. And maybe does some other stuff. Then x prime, y prime, so this is a picture of x of t, y of t, right? Then x prime, y prime, well, it's going to be also two functions of time, right? X prime will be a function of time, and y prime will be a function of time. If you evaluate it at a particular time, like say when the dot is here along its trajectory, if you evaluate it at that particular time, x prime, y prime will give you a velocity vector for which way the dot is going and how quickly it's going that way. So it'll give you two components of a velocity vector in the phase plane. That's what it's doing. Let me give you an example. So here's pretty much my favorite parameterized trajectory. And there's no differential equation here. We're kind of pretending that you already went through the differential equation, you solved it, and this is what you got. This is the kind of thing you're going to get. And I told you if we can, let's package things together, and then I didn't do it. So let's do it. So it's this vector, which you can also call this for short, is equal to cosine t sine t. So at time 0, what value does this take? At time 0, cosine is 1 and sine is 0, so I get this dot. At time pi over 2, I get 0, 1, so I get this dot. At time pi, I get negative 1, 0, so I get this dot. And at time, whatever the radians of this point is, 3 pi over 2, I get 0, negative 1. So I get this dot. And you get, right now it looks like it might be just pinging around from dot to dot, right? But it's not moving in a straight line. In fact, it's going in a circle. If I can draw a circle. And it's going this way around the circle specifically, right? So as you run time forward, it goes this way around the circle. And the way we know it's a circle is pretty much from the definition of cosine and sine, is if you draw a circle of radius 1, let me draw a separate circle of radius 1 here. If you draw a circle of radius 1, and then you put a dot on the circle at t radians off of the x-axis, then what are the x and y coordinates of that dot? They are cosine t and sine t. That's like what cosine and sine means. They're the x and y coordinates of a dot on the unit circle with some given radians. So this is a way of describing a circular path. Okay, so now you can see what I mean by these things giving us trajectories in the phase plane. So this is totally something that you could end up with after solving a differential equation system. You could end up with something like this. By the way, if you want to plot these kinds of things in Mathematica, which you should use some program, Mathematica or some other program, because you have one homework problem where you're asked to look at the plots of some of these. What you can do is use the parametric plot command and do this, put two arguments. So the second argument is what's the parameter and the range that I want it to run. So let's make t run from 0 to 2 pi. And then here you can input this package as a whole. So a list of two functions, one function of t and another function of t. So x of t, then y of t. So here cosine t, then sine t. And then I get my nice circle. It doesn't give me the arrow. The arrow is sort of telling me which way is forward time. But you can fiddle with it to try to get things like that possibly to show up. Yeah, notice if I play it for only from t from 0 to pi, then I only get half a turn, right? T from 0 to 4 pi, that's 2 turns, but that looks the same as 1 turn, right? So when you look at the trajectory, you're not seeing all the information, right? You're just seeing the different values of x and y that get taken, right? The different x-y pairs that get hit. You don't see at what times they're getting hit. So just from staring at this alone, I cannot see, you know, at what time the trajectory reaches here. I just know that it does reach here at some time. So there's some limited information, but that's inevitable. There's 3 variables here, right? T and x and y. If you're going to make a 2D picture, then there's going to be some limitations as to what can be displayed. I saw that there are a few people using this online graphing tool, Desmos, which usually creates some really pretty looking plots, I think, and makes it easy to just like pan and scroll and zoom, basically better than any of those handheld graphing calculators at least. And this seems to work. So I just tried this, just listing what you want to plot in a pair like this, cosine t, sine t, and there I get part of my circular arc. Then I can say where I want t to start and where I want it to end. Let's see, can I type pi? Yeah, cool. So there's my circle there. If I make it run just to pi, then it's like that. Very nice. Okay, but the point of this example was actually to show you what is meant by velocity vector when we take the derivative. So let's look at, let's pick a particular time to focus on. So I'm going to focus on time equals pi over 2. And first I'm going to look at the position. Let me make that be in blue. So the position at time equals pi over 2. I know we pointed it out here, but let me just show, you know, what you would do to compute that. Vector x, meaning the package x, y all together, at pi over 2 equals, and then I plug in pi over 2 and I get cosine of pi over 2, sine of pi over 2, so 0, 1. 0, 1, so that's 0 over and 1 up. So it's there. Okay, now for the derivative. So the derivative is what you get when you take the individual derivatives, x prime, y prime, right? Which is negative sine t, just taking the derivative of cosine t, and then cosine t, just taking the derivative of sine t. So now let's say I want to know what that is at time pi over 2. Then that would be negative sine pi over 2, so that's negative 1, and then cosine pi over 2, so that's 0. So negative 1, 0. And why is that? What does that mean? That means dx dt is negative 1, and dy dt is 0. That's telling me that when I'm here, at the moment that the particle or the state or whatever you want to call it reaches here, at that moment, y is not changing, dy dt is 0, and x is changing in the negative direction at a rate of 1. And if you plot this as a vector, just as a 2D vector, it's a vector pointing to the left, right? This is how you would plot the vector negative 1, 0. It has a horizontal component of negative 1 and a vertical component of 0. And does this make sense pictorially? Yes. If the particle is traveling in this direction, going in circles, then yeah, when it's here, at that instant, its instantaneous velocity is that it's going that way, right? Of course, in the next moment, it's going to change and its velocity will be like that, and then like that, and then like that, and so on. So this is what you're getting when you look at the derivative. This is important to understand because that's what is on the left-hand side of any first-order differential equation system, is these velocity vectors. So what is a first-order system of differential equations, then? It is a prescription for what the velocity of a trajectory in phase space should be, depending on possibly the time and depending on the current position in phase space. If you don't have the time part there, so if I remove t dependence and I have something autonomous, you can still call this kind of autonomous, where the rate of change of the state depends on the current state only and not what time it is. In this kind of situation, you would say the differential equation prescribes for any given point in phase space, for any given point in the phase plane, what should be the velocity for any trajectory passing through that point. So this is sort of a rough summary of what I'm saying. First order differential equation is a prescription of a velocity for the trajectories in phase space. If it's autonomous, if you don't get that explicit time dependence, then for every point in the phase space, pick any point, and the differential equation will provide you with a vector that says, hey, this is what your velocity should be if you pass through this point. So this is sort of the way to think about what the differential equation is. At every point, it's giving you a little motion vector saying, here's how the system is going to evolve if it were here. Here's how fast it changes, and this is the direction in which it's going to make the change. So then, if you fill the phase plane with all these little vectors, then what you get is something called a vector field, which some of you are taking Math 6a at the same time or have taken it, and then you would have seen what is meant by vector field. And that's kind of what a differential equation is, especially when there's no time dependence here, which happens often. Then it really is just one fixed vector field. That's what the differential equation is. And then solving the differential equation is just the process of, I say just, but it might be difficult, but it is the process of basically trying to trace out curves, find trajectories in the phase space that are always tangent to the vectors in the vector field, so that and that always travel at the prescribed speeds. So basically, find curves that go at the velocities that the differential equation prescribes trajectories must go at. All right, so up to this point, since we haven't really seen any examples of differential equation systems, this is probably kind of seeming abstract. That's okay. I want you to get a first look or a first exposure to the idea of how to visualize what a differential equation system is saying in the phase plane. And we will definitely draw pictures a lot and use the phase plane a lot in this course for the rest of the quarter. And so you will get many chances to try to solidify the idea.